Okay, sorry for being late. I'm driving. So first things first, we should decide on which term you would like to have an exam and secondary term of the exam. So if anyone has any idea on which date should take place, please share it with us. The terms are available between 22nd June and 12th July.
Excuse me, sir, for what?
Sorry, I have a problem. University. So, okay, we have to decide on which day would you like to have an exam and the available terms of July. I hope that you can hear me now. Maybe I will type it.
But do we need to decide now, or can we talk in a group chat on Facebook and send you something like an email with the decision?
Okay. So you can just, I mean, I need to deliver such info until Friday, so you have a couple more days just to decide. I mean, it's rather up to you. Which, if you will not decide until Friday, I will select some days for the exam. Also
I have one more question about the exam. If both of the exams should be in between those terms that you send us, or only the first one?
Okay, so let me move to the. I'll double check if I gave you a correct dates. Okay. Oh, yes. Yes. I suppose both. Just give me a second. Both, but the dates are a little bit different. So the dates are. Between those days. 2 days between those terms. Okay, so if you will have some suggestion, you can tell me until the end of this lecture or until for the exam until Friday this week. So I introduce some theorems regarding the linear programming, namely the fact that the optimal solution in linear programming is located at the slide. So we are starting at some vertex, and we are moving to vertices and
Sorry, Professor, but we cannot hear you.
Yes, your voice is constantly being cut off. You are simply lagging.
Are you gonna let the professor come in?
Okay, if the internet connection will drop once more, I suppose that we will postpone the lecture to the next week. Because it doesn't make sense to talk if it's not possible to, if it's interrupting all the time. So I was discussing the fact that that we know that if in some vertex we cannot move to any of the adjacent ones in such a way that we are improving the solution, this is the optimal one. This is the consequence of the convexity of the convex set. The intersection of multiple half planes, half spaces creates a convex set, a polytope, which is a convex set. And convex set, it means that if we select any point in any 2 points in that set, for example, our vertex with optimal value, and any other one, all the points on this line belongs also into that set. And because it's a convex, we can select any other vertex and connect it with line, right? Which is also included in that set because it's convex. So we can also include adjacent vertex. And if this point wouldn't be an optimal solution, it can be possible to move to one of the vertices in such a way that the solution is improved, for example, to this vertex. And because the objective function is also linear, we can move to other vertex improving solution, which is also an adjacent one. So the simplex uses this fact to compute the optimal solution and to reduce the number of vertices which are needed to investigate. So, okay, this is what I mentioned already. So we showed that the optimum is located in one of the vertices of the polytope, and this method operates on the canonical form of the linear programming. On the second lecture, I showed you the canonical form. So this is the form where we only have equality constraints. And it was also described how to convert these other inequality constraints to equality constraints by introducing some additional variables. So after such a reduction, we will probably have a larger number of variables or larger number of constraints, but we have this canonical form, which is crucial for operation of the simplex. So what remains is to define, firstly, how to find the initial point, the first vertex, which is a feasible point, and how to pass to adjacent vertices. What operation should we use to compute what is the next step of the simplex? Because it's easy to compute it in two-dimensional space. However, if there is higher number of dimensions in the problem, it's not possible to draw it, and we have to compute it somehow. So just to recall, this is the canonical, or in other way called a standard form of linear programming. So we have a minimization of the function, and we have a set of equality constraints. So n is the number of dimensions, the number of variables in X vector. A is the matrix of coefficients in equality constraints, which is the size m times n. So we have m constraints. So the rank of this matrix is equal to m, and this number of equality constraint has to be lower or equal than the number of dimensions. Otherwise, if we have higher number of equality constraints than number of dimensions, most likely the solution is infeasible. For example, if we have a two-dimensional problem and we have two equality constraints, so this is one constraint, this is a second constraint, we already have only one point, which is a feasible set. If we add another equality constraint, then our feasibility set is empty. So it's an empty set. And none of the points is a feasible one. That's why we have such a constraint that the number of equality constraint assumption that the number of equality constraints is lower or equal than the dimensionality of the problem. So let us introduce some definitions. N is called a dimension, M is called a rank of the problem, and any X satisfying such an equation, set of equations, equality constraints, is called a feasible solution. And suppose that the rank of the matrix A is M, so we have M rows, and we have N columns in this matrix A has M columns and N rows, M rows and N columns, and we can choose from this set. We know that M is lower than N, the rank of this matrix is lower than the dimensionality. We can select from these columns M columns that are linearly independent. So they are forming the non-singular matrix. Non-singular means that if we calculate the determinant of this matrix, it's different than 0. So such a matrix, such selection of columns, this is a square matrix. We have the same size, the same number of columns and the same number of rows, is called a basic matrix. So this is a matrix, this selection of columns from our coefficients in equality constraints, which forms a non-singular matrix, and such matrix is called a basic matrix. So for example, if we have such a system of equations, we can select a basic matrix, which is formed from this column and this column, for example. So such a basic matrix has the determinant is equal to -2 plus 6, right, is equal to 4, so it's different than 0. But we can select 5 other basic matrices as well. So we can, for example, consider this row, and this column, and this column. So this would be our basic matrix, or this column, and this would form a basic matrix, right? So when we extract such a basic matrix, we divide variables into two subsets. The variables which have coefficients included in this basic matrix are called basic variables, and variables which corresponds to the columns which are not included in basic matrix are called non-basic or free variables. So if we go back to our example, we have this system of equations. We select two columns. They are forming the basic matrix, and the basic variables are x2, because this is a column with x2 variables, and x4. So this is our basic variables, vector of basic variables, and this is our vector of non-basic variables. And we can express this system of equations using such a matrix notation. So AX is this system of equation, right? Is exactly AX equal to B. This is the matrix, these are the vectors. So AX is equal to B, our basic matrix, multiplied by basic variables, plus some other matrix B prime, such that if we add those two terms, we obtain the vector B of free variables. So if we multiply this equation,
Hello? I think your voice got cut off again.
He's done.